Hey everyone, we're going to do a short video on Workshop 3, Balancing Redox Reactions. Just wanted to remind you or kind of reiterate to you some things about submitting your assignment. I didn't give you any space to do your work within the lab manual, so just show your work on a separate sheet of paper and then you can submit that work. Make sure you're legible so that I can read what you're doing, box your answer, and make sure you stay organized, which means put your problems in order of 1 through 18 and make sure that they are all in the correct order all the way through so that I can find your questions and answers easily. So what we're going to do really quick is we're going to go through the stepwise process of balancing redox reactions in acid and basic solutions. I got this 9-step kind of list from your textbook, and that was in chapter 4 section 2, and it's a very good list that really breaks down what you're supposed to do to balancing a redox reaction, and it encompasses both acidic and basic steps depending on what your redox reaction happens to be in solution. Step 8 is what you would add if you happen to be balancing in a basic solution. Otherwise, you go 1 through 7 and then skip to 9 for acidic solutions. So we're going to do 2 problems. We're going to do problem 1 in acidic solutions, and we're going to do problem 2 in basic solution. Okay, so let's go to problem number 1. I'm going to go ahead and copy and paste this down here, and we're going to work through here. Sorry about that. And the first step that you need to do is determine the 2 half reactions. You'll need to know what's reduced and what's oxidized. And to be able to do that, you need oxidation numbers. And so those 2 things, reduction and oxidation, are the things that you'll need. So we'll go through and figure out oxidation numbers for everything, and that'll kind of tell us what's reduced and oxidized. Anything that's in elemental form, like Br2, has an oxidation number of 0. Oxygen here is -2. There are 2 of them, a -4 total, so that means sulfur must be +4 to make that sum up to 0. We've got, obviously, bromide here is a -1, and then you have -2 for oxygen. Here in SO4, 2-. That means -8 for all of the oxygens total, and since the whole thing sums up to -2, sulfur must be +6. So we see that sulfur goes from +4 to +6. That's oxidized. And bromine goes from 0 to -1. That's reduced. So those will be the items that you use to make your half reactions. So we're going to write down our half reactions, one on each side. We'll do the reduction side on the left and the oxidation side on the right. So you'll write the species. That means it's the item that contains the thing that's reduced or oxidized. And then the reduction, it's Br2 yields Br-. And then the other oxidized reaction is SO4 2 yields SO4 2-. Okay, so now these are both of our half reactions. We've gone through step 1. Check. Now what we want to do is balance all of the elements except oxygen and hydrogen. So really simple. What you do is you look at the substances. You have 2 bromines here, only 1 here. So I'm going to go through and put a 2 to balance this side. So over here, for our oxidized reaction, we've got 1 sulfur and 1 sulfur. Guess what? That's already balanced. Remember, we're only doing any element other than oxygen and hydrogen. So that is step 2. Check. Now what we want to do is balance oxygen atoms by adding water molecules on the side of the reaction that will sum up both sides to be equal in oxygen. Well, it turns out that this first reduction equation has no oxygens in it, so we won't have to do that step for that half reaction. This one does. It's got 2 over here and 4 over here on the right-hand side. So to balance those, I'm going to put 2 water molecules because that now gives me 2 additional oxygens. Now that side on the left side sums up to 4 total oxygens. So that's how you do that. Now, if you put water molecules on one side, so that's step 3, right? Then you're going to have to, because the water molecules has hydrogen in it, you're going to have to balance those hydrogens as well. And we do that by adding hydrogen plus ions. And so since we didn't add any water molecules to our reduction equation, we won't have to do step 4 as well to it, but we did that here on the oxidation equation, half reaction, and we have a total of 2 times 2, that's 4 hydrogens. So that means on the other side over here, I'm going to have to put 4 H pluses to balance those hydrogens out as well. So that's now step 4. Now what we want to do is balance the charges of each side of the reaction in total using electrons. Now keep in mind electrons are negative, and so they have to sum up both sides to the same value. So I do kind of like, what is the charge of this side versus the charge of this side? Over here is 0, and on the right-hand side it is -2. That means you have to take into account the coefficient because you have 2 Br minuses. So I need these guys to balance and be the same charge, but I can only use something that is negative. Well, that means I'm going to have to add 2 electrons onto the left side of that reaction. So now that actually sums up to -2 over here. Now they're both the same. Same thing over here. We're going to look at both charges on both sides. Right now on the left of this reaction it's 0, but on the right hand side this is 4 pluses and 2 minus. That means it's +2. Okay, well if it's +2 and 0, the only thing you can do, remember, is add negative charges, negative electrons. So how do you make 0 and +2 come to be the same value? Well, then you're going to have to add 2 electrons to the right-hand side. So I'm going to move these over just a little bit, give me some space. I'm going to add 2 electrons. And so now this charge no longer is +2, it is now 0. And so now they're summed up as equal. Okay, so that is step 5. We've got them balanced. Now what we want to do is we want to make sure that each half reaction has the same number of electrons within them so that their total value of electrons is equal within their reaction. So if you'll look over here, this guy has 2 total electrons in this whole reaction, and this guy has 2 total electrons in this one. So they're balanced and the same. If they weren't, what you would do is use the lowest possible integer and multiply by all of the coefficients within a half reaction to make it where these guys have the same number of electrons. Okay, but this guy happened to be just fine the way it is, so we don't have to change anything for that. So number 6 is done. All right, number 7. Add the balanced half reactions together and just simplify by removing anything that's similar. So what we're going to do is we're going to take all of the left-hand side of this reaction, the left-hand side of that one, and add them together. So this is 2 electrons plus Br2 plus 2 waters plus SO2 yields, and all of the right-hand side, 2 Br minuses and everything over here, and write those down as well. So 2 Br minus plus SO4 2 minus 4 hydrogens, and 2 electrons. And what you do, once you have added those together, it says remove species that appear on both sides. So anything that appears on both sides that is literally exactly the same down to the charge. Well, the only thing that there is that is available that looks like that is our electrons. 2 electrons on both sides. Everything else seems to be something slightly different, maybe a charge or kind of how many oxygens or something like that. So we're going to take and cut these out, and then what is left over? This is your reaction. That is your balanced half reaction. You want to just check and make sure, because this is an acidic solution, just check and make sure that the number of atoms and everything are balanced. And so again, just you have 2 bromines over here, 2 over here, 4 hydrogens, 1 sulfur, and then a total of 4 oxygens. So that's your balanced redox reaction. Okay, so that's how you do it in acidic solutions. Let's try this again with a different reaction, but in basic solutions. So I'm going to take and remove all of this. And here we go. We're going to work with this particular reaction here. And we're going to go through our steps again as well. Okay. And this time, keep in mind that when we're doing this, we're going to add step 8 into this whole process. Okay. So, first things first, let's determine oxidation numbers, everything. So something that's in elemental form is 0. You have -2 for our oxygens. This is going to give our nitrogen a +5. You have zinc is already your +2. And hydrogen over here is +1. This is one weird time in which a substance has the cation written second and the anion written first. Oops, I'm sorry. That should be -3. Okay, so what has changed? It turns out zinc has gone from 0 to +2. That means that that has been oxidized. Nitrogen has gone from +5 to -3. Let's remove that real quick. To -3. That means it's been reduced. Okay, so you can write the species that contain both of those oxidized and reduced elements in half reactions. So let's write the reduced side. NO3- yields NH3 on the left. And then let's write the oxidized side, zinc to zinc 2+ on the right hand side. Okay. So now what we want to do is step 2. We want to balance the elements other than hydrogen and oxygen. So it looks like your nitrogen 1 and 1 is balanced. Zinc 1 and 1 balanced. So great. Let's move on to the next step. We want to balance oxygens using a water molecule. Well, you see 3 oxygens here. So we're going to put +3 waters on the right hand side. And then we're going to use hydrogens to balance the hydrogen on the left hand side. So we're going to put +6 H pluses because there were 6 of them, or 6 hydrogens. We don't need to do that for the reaction that's oxidized over here. There are no oxygens, so we won't need to add any waters. Therefore, we won't need to add any H pluses. So far, we've gotten every element balanced. What we want to do now, and this is moving on, I'm kind of not showing you the steps here, but we've gone through steps 1, 2, 3, 4. What we need to do is balance our charges using electrons. So we're on step 5. So we're going to take and count the total charge, left and right side, of each half reaction. So we've got +6 and a -1. This is +5 for the left and 0 for the right. And then we have 0 and +2. And so what do we do? How do we make these equal? Remember, you can only use a negatively charged electron. So to get +5 and 0 to be equal, I would have to put 5 electrons on the left, and then for our oxidized half reaction, we would put 2 electrons on the right. Okay, so that's step 5. Now this is where step 6 is really going to come in. We didn't really have to do step 6 in the previous problem, but we do on this one. So we need this integer, and this integer to be equal to one another. And so what can you do to 5 and 2 to make them both be equal values? The easiest thing would be to multiply them by each other. So I can make this 5 a 10 by multiplying it by 2, and I can make this 2 a 10 by multiplying it by 5. You know, if you do that to one thing within a half reaction, you must do it to everything in that half reaction. So if I multiply this times 2, that means every coefficient within that half reaction also has to have a times 2. And then the one over on the right-hand side, our oxidized, has to have times 5, times 5, times 5. And so let's rewrite these with our proper oxidation, or our proper coefficients. This will be 12 H pluses, 2 NO3 minuses, 10 electrons yields 2 ammonias, plus 6 waters. That's 1. And then you have 5 zinc yields 5 zinc 2 plus 10 electrons. And so now you can see that this electron and this electron are similar. Move on to the next step. Got that? We're going to add those guys together, and then we're going to remove anything that's similar. And so we're going to write everything that is on the left-hand side here and the left-hand side here together. So this is 12H plus 2 NO3 minus plus 10 electrons plus 5 zincs yields 2 NH3. This is everything that's on the right-hand side of both reactions. And then we're going to remove anything that's exactly the same on the left and the right. This and this are exactly the same, and I do not see anything else that looks exactly the same. So we're just going to cut those out, and what's left over is what we've got so far. And in fact, just rewrite it. Sometimes it's easier to just rewrite so that you'll have everything step by step written down. Okay, so now that we've done that, and remember, we're now in a basic solution. So remember, we need to now do step 8. So this says, for the reaction occurring in basic media, carry out the following additional steps. Add OH ions to both sides of the equation in numbers equal to the number of H plus ions. Okay, so let's look at this. So here's our reaction right here. We're looking at this. Okay, well, how many H pluses are there? Well, there are 12. So what I'm going to do is I'm going to add, and let's do this in a different color. We're going to add to both sides, it said to both sides, the same number of OH minuses. OH minus, so that means I'm going to have 12. Okay. Now, and then what it's going to say is part B. It's going to say on the side where you contain both H pluses and OH minuses, combine them to make the water molecule. So that means that this particular part right here is now going to become water. So you have 12 H2Os here. Okay, so we're just going to essentially remove that and put 12 H2Os in its place. And the last part is simplify the equation by removing any redundant water molecules. This means if you look at this reaction, now you have 12 waters on the left, and see before you had 6 waters on the right. That's redundant. Okay, so you remember we're trying to simplify to the smallest number of each type of element or compound or substance on both sides. So that means that the waters over here on the right-hand side are going to go away. And because 6 of them went away here, I can take 6 of them from here, and that leaves me with 6 left over. So what is officially, moving on now to the last step is just check and make sure everything totals up correctly. And so this particular reaction, I'm going to kind of move all of this stuff up so we have some more space, will then be a total of 6 waters, 2 nitrates, 5 zincs, which yields 2 ammonia molecules, plus 5 zinc 2 pluses, and 12 OH minuses. This is now your balanced reaction in a basic solution. So that's how you go through that process. What I want you to do now is you have several problems in a problem set, 1 through, I think it's 18. You have 3 pages of that. I want you to work all these problems on a separate sheet of paper and make sure you're labeling them so I know which one is which, and put them in order, and then submit that as your problem set in Blackboard. If you have any questions, send me an email or post a comment in YouTube, and I can get back to you as soon as possible.